the people that I might want to fail, just for fun. just for fun. I have to fail at least one person every semester just to keep up my reputation. and okay, let's see if I can find. There's Project for Help. Um, Gosh, do any of you see any other Project for Help? There's Project for Help. Oh, and here's Project for State Table. Okay, I had a student or two ask some questions, and I tried to help, and I don't think this has got any names on it, but I had more than one with very similar questions as to this. So I'm assuming that many of you are doing your project like this. Your state A, you've called 1. Your state B, 2. Your state 3, C, 4. And state D, 8. I mean, most of us do that in sequence. It doesn't have to be. It could have been, 1, 4, 8, 2. It doesn't matter as long as each of these current states are unique. That's all they have to be. And since it's one hot encoding, that means that right there, when you have, let's see if I can call that up. I should sit down. If I don't sit down, I think I might fall down. Okay, so let's look at Project 4. As soon as you look at this and see the actual homework, there it is, 4 states. As soon as you see that, you know you've got 4 flip-flops. You have to, because it says one hot encoding. Okay? One hot encoding, again, means that the flip-flops have one flip-flop is high for each particular state. So, here's the one for state A, here's the one for state B, here's the one for state C, here's the one for state D. Like I said, these could be mixed around. It doesn't matter as long as each one's unique. And as long as there's only one 1 per flip-flop. Or, yeah, 1 1 per state variables. Now, I'm not, there may be, but there's problems in here. But he sent me this, and what I was getting at is more than one person has sent something like this, asking questions. That's just great. And what they've all done seems to be this for state A, B, C, and D, and that's fine. I'm just saying that those could be different if you wanted them. Okay, then here's R, S, and T. For state A, if you look at it, there are 1, 2, 3 transitions exiting A. So there should be 3 sets for variables here. This one says S equals 0, has nothing to do with T. So there's one in here that says S equals 0. There's one in here that says S equals 1 and T equals 1, and there's one that says S equals 1 and T equals 0. So in both cases, S equals 1, but it's T that's the deciding factor here. So we got S is 1, T is 1, S is 1, T is 0. Okay, for state B. Let's just look at these columns, and then we'll look at these, and then we'll get over to this. Okay, state B has this exit and this one exit. Everything else is coming into it. So here we got R0 and here we got R1. R is the only input variable that has anything to do with state B. Exiting state B. We don't really care what's making it come into it. Okay, state C, we have 1, 2, 3 transitions exiting C, and that's R equals 1, T equals 0, R equals 0, and T equals 1. And then this one is kind of a messy one, okay, because it has to be R equals 0 and T equals 0, or R equals 1 and T equals 1. So we've got, there are several ways of doing this, but state C, we've got R equals 1 and T equals 0. That was R equals 1, T equals 0. We go to state A. That's fine. The next one here, where was I at? Here, C. R is equal to 0, T is equal to 1. R0, T1, we go to state D. That's fine. The next one was this and or thing. There was a whole lot going on there. So the way this particular student decided to show it was the zeros and ones both on this line and state B on this line, because both of them go to state B. That's fine. Either one of those is fine. Okay, and finally we get to state D, and there was no condition here, so all we had to do was say if you get to D, doesn't matter what any of the inputs are, the next state is going to be A. So in this one problem, I've pulled in just about everything I could pull into it, right? An unconditional, several ands, a couple of ors, several things that I could pull into it. Now, the question the student was asking, he had everything right as far as the one-hot encoding and as far as current state and next state. You can label these things, these and these, anything you want. It doesn't matter as long as you can keep track of them. If I was setting up a truth table, or if I was setting up current state, next state type things, a lot of times I would say A is the most significant, then B, C, D, E, F, all the way to where I got the least significant variable. So in this case, we needed 4 because we had 4 states, one hot encoding, 4 variables. So he has A, B, C, and D. I would have done it almost exactly the same way. Okay. The thing is, you got to make sure that you're keeping this straight from this, and that's one of the difficult things. We're using A, B, C, and D everywhere in digital, and you just got to make sure that these are, you can see that they're different from these. And he's done that. That's fine. You could also say this is state 0, 1, 2, and 3. That's fine too. They don't have to be A, B, C, D, E, F, right? And I might have to check my email because there was another problem that's very similar to this that was emailed to me. I was told that we could look at because of the K-maps. Okay, so everything looks okay for current state, next state, right? And what I would do is, before I went any further, I would go back and forth between this diagram. Actually, be easier for you guys because there'd be two pieces of paper right there in front of you, or a piece of paper you're working on and this screen. But just make sure you've got A, and that it goes to state A, or it goes to state B, or it goes to state C. And that's what this is, A, B, and C. And then put in the variables what those conditions are. Okay, now, the next part. This is where I think it starts getting a little confusing. I would have said this is D3, D2, D1, D0. That's me. He had D1, 2, 3, and 4. That's fine. As long as you know that this D is the input to this flip-flop whose output is QD. Okay, so every one of them has a flip-flop whose input is D something and output is Q something. This is the current state of that flip-flop. This is the next state for that flip-flop. Okay, so if what probably the easiest way to do this is looking at, here's A, the most significant digit. Here's D, D4, which is going to be the most significant flip-flop, or the answer, the flip-flop that has the most significant digit for the answer. And here we look, and no matter what, when we go from the current state to the next state's always zeros. And we should do one with, at least one with JK, just so you can see how all that, but there's a lot more work with JK. That's why I've gone to D. Anyway, here's all zeros. This is 0. That makes sense. Okay. The next one, we see a 1. What we should do is look at, for this column, we're working with D3 over here. We look at this one and say, how would I write an expression based on these inputs that would give me this 1? Well, this is not it. I would write not S right here. This is not what I would write. That's not really correct because we don't care what T is. It would work because it's not S. But what should really be there then is not S and not T, or not S and T. And then if you reduce that, it would be not S. Okay, so that's all it should be. D2 here goes with QC. I see a 1 here. So I should come over to these inputs and see, how can I write an expression based on these inputs to get this 1? Well, that happens when S is 1 and T is 0. So this is not correct. It should be S and not T. He's got S and T. I'll have to text him back later. He said, okay, I'm sorry. That was real interesting. I had recommended for somebody for CP, and they said they keep getting this resumes from this one person, but they think the name is this one guy I said stay away from. He's freaking nuts. And that's who they think it is. And they're like, help us out. Is this guy the nuts guy? Or is this guy okay? And see, I think his name was Pierre. And no, his name wasn't Pierre. Uh, I'm sorry. I'm sorry. I was really just kidding. As long as I'm teasing you, I'm not. You're not on my short list for being the one that fails my class. So you're all right. Okay. So here we're in the fourth column, and we see QD. It's associated with this flip flop, and we see this one is going on when S is 1 and T is 1. So again, this is incorrect. That should be S1, T1. Now, what I did was trying to send, now that's complicated help when somebody sends me this table and says, can you help me out? So this is what I had to send them back, which was D4 is correct. D3, blah, 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 D2, blah, 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 D1, blah, blah, blah. Okay, why they were incorrect and what should be in that place. So I was able to help them out at that point. So let's look at the next one. Let's make sure it's right first. We've got state B. If R equals 0, we stay in state B. If R equals 1, we go to state C. That's all that we got going out of state B. So here's what we have. We've got only R. If R is 0, we stay in state B. If R is 1, we go to state C. And honestly, state, current state, RST, and next state are all you need. Possibly output if there's an output column. But that's all you need for the VHDL. Okay? You don't need the column with the flip-flops. Okay. And this says flip-flops. It probably should say registers or memory. Anyway, here we go. The first column, it's the next state has to have 0 no matter what. So D4 is 0. Down here at the least significant one, it's always got to be 0. So there's a 0. Here, now, I mean, you can do this several different ways. You can go, oh, look, 0, 1, 0, 1. So that's the same as R. Another way, because sometimes these start getting complicated, I just look at where's the 1 and what's the expression for 1 based on this. Well, this is saying R equals 1, or the state variable is R. Here, the 1 is up here, which is not R. Okay, inverse of R. So that's this right there. So that's good. So now we've got the first two columns going. Here's state C. State C was that one that had this tricky one in there. But we've got state C can leave with R1 or R equals 1 or T equals 0, or and T equals 0, R equals 1 and T equals 0. That takes us to state A. So all that's correct. Then for C, coming down to D, we've got R equals 0, T equals 1. So we've got from C to D is R equals 0, T equals 1. And then we got this one going from C to B. And that says R is 0, T is 0, or R is 1 and T is 1. And then we get over to state B. Okay, so that's all this in these 4 columns is fine. Here's where the problem is. We've got 0, 0, 1. Well, this 1 I should look over here and say, what expression can I come up with for that 1? And it should be not R and T. Well, that's fine. He's got it fine there. There's nothing wrong with that. Not R and T. On the second one, they're always 0. Now, because this is one hot encoding, we'll never have a column that's all 1s. But in your next one, in Project 5, you may have a column that's all 1s. This one you won't because of one hot encoding. So anyway, all 0s, so this one's 0. This one, we have the 1 right here. Now that's the 1 we got to look over here. And this is actually not R and not T, or R and T. So that's a fairly long expression that has to be in here. So it'd be not R and not T, or R and T. Finally, over here, we have the 1 up in this area, and so R is 1, T is 0, so we got R, not T. So he's asking questions on the ones that are correct, but they're correct. It's this one that's got a problem, and these 3. Okay, the last one, the or unconditional one. That one's the easy one. R, S, and T don't matter. We got he's chosen, and I would have done it too, to have 1, 0, 0, 0 as my state, and it goes to the next state all the time without any inputs. It goes to state A, which is 0, 0, 0, 1. So all we have to do is put 0, 0, 0, and 1. Okay? So, there we go. We got all that. I've explained all that in this document, and then that's probably actually hard to read. This is the one that we need to look at next. Okay. Now's the time that we come up with these flip-flops, or these K-maps for right here. And I kind of have done them, or I'm not sure they're exactly the greatest way. But this is going to be the flip-flop that he's got labeled D4s. Yours might be D3, it might be DA, it might be the top D. I don't know, whatever you want to call it. But normally here we have, if this was a 4x4 K-map, we would have AB across the top. It's the way I do it, so I've been doing it that way all semester. And CD down along the sides, right? You guys, a lot of you in your community college had AB down the side and CD across here, right? And if you were here, you were lucky enough to have me for digital, I think. No. Some of you had somebody else for digital, so you weren't lucky enough. Ask Isaac. He was lucky enough to have me, and after class he'll tell you that had nothing to do with luck. That was probably one of the worst semesters of his life. First time I had taught the course. I don't care what the course is, first time I screw it up. Okay, so it wasn't that bad? Okay, you're still getting a good grade in this class. So we got A, B, and we had AB 0, 0, 0, 1, 1, 1, 1, 0. Go back and look at all my earlier PowerPoints about flip-flops, and you'll see that AB was always like that. CD always was 0, 0, 0, 1, 1, 1, 1, 0. So now if I put a number on the cell, I could go back and get those, and it would be cell 0, 1, 2, 3, 4, 5, 6, 7, right? 8, 9, 10, 11, and then 12, 13, 14, 15. Now, when we look at this, we've got, I mean, this is the one that we're working with. This is the cell number we're working with. This is cell 1. We're going to put a 0 in cell 1. So we put a 0 in cell 1. Okay? Then this is cell 2, and I put a 0. Okay? Here's cell 2. Remember, it's 0. You can look at these variables too. 0, 0, 0, 0. This one's 0. 0, 0, 0, 1. This one's 1. This one's 2. That gets a 0. And 3 is a don't care. Then, for 4, we have not R and T. Now, that's not what we have written over here. Or yes, we did. Not R and T. This was right. This was the one that wasn't right. So, not R and T. And that goes here. And then, in this last one, a 0. So, a 0 goes in cell 8. We'll get a 0. All the rest of them are don't cares. All the rest are don't cares. And you know what? Since this is 1, 2, 4, and 8, for every one of your 4x4 K-maps for this problem, all the variable or all these cells that have don't cares in those other ones also. They're all will only have something written in here, 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 and here. And that's the one I've got emailed to me, right? And I could, let me, okay, I've got a, oh, okay. Sorry, I end up telling everybody who you are, and that's not what I meant to do. Where'd it go? Yes, we want to open it. Okay, so here's all the K maps. All right. So this is a 0. We're not gonna combine that with anything else. So is this 0, this 0. What I did on this was I combined this particular expression, not R and T, with, this would normally be B, variable B. Well, this will be QB for this particular one. So we got D4, that's the flip-flop I'm writing it for, is equal to QB and not R and T. One big expression. So this is what we're going to, when we draw this circuit out, we're going to have QB, the output from that second one, coming back into an AND gate, not R coming into the same AND gate, and T coming into the same AND gate, and the output of that AND gate goes to the input of D4. Okay, now, can you say that again? I don't think so. I said that Damn, what did I say? I'd say the output of this particular flip-flop that we're calling QB, which is probably the second flip-flop, it's going to, that output's going to be fed back to the input of an AND gate. Not R is also connected to the input of that AND gate, and T is connected to the input of that AND gate. So it's a 3-input AND gate. The output of that AND gate goes to D4. Okay? So Q4 will have the output from that. Now, I've been saying that in this, that the output is just what? The output of the system or the outputs of the flip-flop. What I mean by that is whatever you call those outputs, they're just going to be, each one of those are going to be tied to, where did I put it? It's probably here. Okay. This doesn't show it. Each one of those are going to be tied to, the output of each one of those flip-flops are going to be tied to one of those output type flags in Xilinx, right? To one of those output type flags. And so in your ISIM, your inputs to this system, you're going to have one for reset just to get it started. I don't show it in anything, but you're going to have to choose an arbitrary reset in here. And then your other inputs are always going to be R, S, and T. And then your outputs are going to be these flip-flop values. One of the outputs will be QD is a 1, the rest are 0. This one, QC, is going to be a 1. You're going to know you're in state B then. Here, you're going to know you're in state C because that particular flip-flop is a 1. And here, QA, this flip-flop's going to be a 1. Now, some of you, if you're calling this flip-flop A, B, C, and D, you might have flipped these around so that QA went with state A, right? You might have done that. I don't know. It doesn't matter as long as each of these has a unique value. Okay. So that was the same thing on this one. This student had done this, then got down here and did the same thing, and then came up with this for all the inputs to these flip-flops, and noticed he looked at them as D0, 1, 2, and 3 with Q0, 1, 2, and 3, and that's not confusing with A, B, and C, and D. So anyway, all of these are correct, right? We got 0, not S, and then not S. I'm sorry. This one, what? That should be S and not T. So this one should be over here, and then this last one should be S and T. Right. Okay. Then on this one we should have 0, R, not R, and 0. This one we have not R and T, 0. Here we have R and T, or R, not R and not T. And here we have R and not T. And here, unconditional, we got just 0, 0, 0, 1, whatever this was supposed to be. So those values then come down here. So in each one of your K-maps, you could have, let me go back in this, depending on what you're putting in this cell, and in the one that he had, this one there was 0, 0, and this was not S, and this was R. So I could change those, but you're either going to have this grouping, or let me see, I'm going to insert, where the hell did it go? This is this new stuff, and I don't like it. It's supposed to say, is this, now they're calling them illustrations, online shapes. What the hell? That was kind of stupid. Illustrations, shapes, and I like the rounded corners. Okay, so if there was a value in here, this would be the grouping, okay, and that would have shape outline, we'll keep it be shape fill of none, okay, so that grouping, or we could have this particular grouping. Where is it? This is going to come over here. I'm sorry, guys. This particular grouping, which would be D in here, right? And that one's outline should be something different. And then the last one that you could possibly have is here. And that one, the shape outline, let's call it purple. Okay, so those are the four. That's nice the way that worked out, right? And so if we go back and we look at this, we'll see that those are the only possible groupings he's got. These 8. Now he could have chosen just 4, but then that's not a minimum, right? And then he's same here, could have chosen just these 4, or just these 2, or these 2, or this one and that one, but then that would not be minimal. So may as well make it all 8, and that gives us C and R, and then you got to look at what was C. Well, C was Q1, so Q1 and R, and this was D, and that's Q0 and not S. Okay, and then we got the down here it's still one of those 4 groupings, and over here it's one of those 4 groupings again. Okay, and some of these, this is a little complicated for hook. It's not that bad, but it's hooking up, 3 input AND gate, and then ORed with this 2 input AND gate, and then you got this 2 inputs, 2 inputs. They're ORed together, and then bring that one in. That one gets to be a little bit complicated, but you should be able to do this. We've been doing all this practice in Xilinx up to this point in both the lab and classes. You should be able to knock that out without a problem. I hope, right? Then, okay, so those are the 4 that you could possibly have. Any questions at this point? Huh? Okay.
What's the point of doing all this kernel map stuff? Because you could just go down the columns and get the equations, right?
Under the columns and get the equations. Just go in here. I mean, you'd have to be pretty good at this to be able to.
Really, I thought it was easier. If you just go, you should have said to do it last class. You just do like D1 is, and you go from the side,
Okay, I was doing this. I was saying, if we look at these, this looks like S naught, but that's not what he has here, but that's what this should have been. But to come up with the whole K-map, I don't know that, because I have to come up with this, and these flip-flops are all going to be possibly coming together to create the output of those of that memory. If we go back and look at where have we been looking, finite state machine design. Okay, let's do this. And when we start looking at this, we see our input logic is fed to the flip-flops, and then that's fed back. The outputs of those are fed back to this input logic and to the outputs. Well, our outputs are going to be taken from right here. In other words, this is just going to be wires through here. But there's that having this output from the flip-flops fed all the way back to the inputs with our inputs makes that a little complex. Now, for this particular one, maybe not, because of the way that this worked out. But in your next one, in state or in project 5, where if you and most people do choose the vending machine, because I've got a pretty good example out there. But you've got so many that it can get a little complicated. Now the next one, you don't have to use any K-maps because you've got just the VHDL, and really in the VHDL you don't have to specify any kind of flip-flops. You just tell it, if I'm in state A and S is 1 and T is 1, I want to stay in state A. You basically say that. So yeah, you don't need any of these columns, and you don't need any of the K-maps or these expressions. You let Xilinx come up with that. And I don't think, well, I think in the old class, when that other guy was teaching it, he did have a very similar problem to the candy machine, and he made you do it all by hand with flip-flops, and then in the lab he'd have you hook it up. And I tell you what, that was the meanest thing he could have done to students. And he laughed and laughed and laughed. That's incredibly difficult because there's so many places to make a mistake. Doing it in VHDL is not anywhere near as difficult as the other one, but it's still going to be a little tricky. You're going to have some outputs that are bad. But anyway, if you can go right from here and go straight to the expression, more power to you. Seriously, that's great. For me, I have to do it this way. Okay, any other questions? No, really? Well, I've still got almost 30 minutes, so I'm not going to waste it. That's a lot of minutes. You guys should have had some questions, right? Here they come. It's that complicated that you got to bring it to me.
The implementation, like the state machine. Or like we'd have a deep flip-flop and then a series of gates, or do you just want us to just put it into VHDL and be done with it?
For which one? No, for 4, you're supposed to have both. I mean, it says in here you're going to do this. You're going to use negative edge trigger D flip-flops. You must include the Carnot maps and state equations, And then you're going to come down here. So you're going to put all that in Xilinx, and then you're going to write the VHDL code. So you're going to do a lot.
Yeah, but is that effectively how you do it for implementation? I will do something crazy.
No.
So you want schematics as well as the module?
That one, I can't just look real quick at something like that and say, yes, that's exactly right. If it's not, then you'd be looking at me and say, wait a minute, you told me it was. Wait a minute. All of a sudden there are a lot of questions. Let me come back to, wait a minute. I don't want you, to lose all the blood in your hand and have it fall off or anything like that. Okay, so let's look at this. We've already gone through this. For this one, all we had to do was come up with, I'm going through all this stuff here, but that's all I had to do. Where was that flip-flop? Right there. So, see, I saw that other flip-flop in yours that's facing the other direction. That messed me up. Okay, you had two flip-flops that are in the same direction as mine, but you had one where it was going this way, and that kind of messed me up. VHDL, and then we did this one, and again, we've got all this crazy input and then some flip-flops over here. Now, I don't care if you've got a flip-flop pointing the other way. My point is that all the way back at the very beginning of these slides, what I was trying to get across here is this is the basics of any state machine. You have inputs, like in our case, in this last one, RS and T. We've got something here that's remembering our last state, so that because RS and T in these, we could have state 1 and Rs1, so we go over here, but state 3 if Rs1 goes somewhere else. So it can, we got to remember what state we're in, and then move, and then look at those inputs. So I can't just look at a drawing real quick and say, oh yeah, that's fine, that works fine. And if you guys can come up with other ways of doing it, what I care about in the end is your simulations show that for this, that you can go through all those states with those inputs. So you got to have one. You got to tell me one's my random reset. I'm going to make it D, or I'm going to make it A. Most of you will choose A. Then you've got to put in inputs to stay in A. You got an input that takes you to B, an input that keeps you in B, an input that takes you to C, an input that takes you back to B. Oops, we've already been here. Got to come back to C. Go to A, go to B, go to C. Oops. Go to D, and then back to A. But you have to go through every one of these transitions to prove to me that your state machine works. All right. You had a question.
Was we doing in a Xilinx, we simulating schematics and then doing a test bench, the result, and then doing it again with a VHDL code like a module, test bench code, and a result.
Yeah. That's why I've been trying to push people to get started. There's a hell of a lot to do on this one. So you're doing state machines for the first time, right? And you have to develop all this. I said I want to see Cardinal maps and state equations. I want to see the schematic capture. I don't want to see the one generated by Xilinx. I want to see the one that you created based on these K-maps and state equations and state tables and all that. You got to create a test bench to verify. Now, I would do that test bench in such a way that it could be used for either one. That's how I do it, so I only have to have one test bench. And then turn around and write the VHDL code. In fact, here I tell you to use the same test bench. Or no, I tell you to use that as a model to create a new test bench. Okay.
Like a drawing the schematic by hand, or be putting it in?
No, you're putting it. Use Xilinx schematic capture to input the circuit developed by you.
Not generated by. Okay.
And then you got to look at the schematic and VHDL outputs and show me that they agree.
So it's like project 1 and 2.
Yeah, this is like a whole bunch of stuff. I wouldn't get started drinking until it's done. Okay? Then you got to show me the complete VHDL. You got to comment it where appropriate. You got to show me all your schematics. You got to show all the test benches and results. And here, I mean, you got to, that says what to have in the report, but it also says up here, you must include the Carnot maps and state equations. So read this real carefully. There's a lot you have to do in this.
It's not bad till you have to write that VHDL code.
The VHDL code is actually the easier part. Now, if I were you, since you're having trouble with your act, I'm thinking you're saying I'm having a little trouble with that.
Yeah, because it never works out right.
Okay, then look at that. You should be able to go through the VHDL code or straight by. Let me go back to Moodle here.
Oh, I mean, I understand what you do to make it and how you make it and everything like that. I'm just saying it's always a pain in the ass to do the VHDL code because it never works out quite like you want it to do.
Okay.
Because it always mixes up your inputs.
Okay, and another one is save everything often, right? Or it's going to mess up there.
And mine's been having a problem here lately where it'll like let me make one test bench, and then when I go back and try to edit my test bench, it disassociates my test
Okay,
benches with my
then,
circuit and all that stuff too.
and I know Xilinx is not meant to work on this Mosaic machine the way it used to. So they moved it over to the Linux machines.
Well, I've been working on it on the computers in the lab, and it'll disassociate my file.
Right.
Is there like something I have to show?
Well, it's not meant to work on any kind of a network. It's meant to work on a single machine.
Yeah.
But anyway.
I have to show it to you because it's a mess.
But what I was going to say is you should be able to go to your VHDL basically from this or from that other table. And if you can have that done before lab tomorrow or by the middle of lab tomorrow, then or anytime tomorrow, I should be here all day. I got an 8 o'clock class and then a meeting I'm supposed to go to, and then I'll be in my office except for lunch up until lab. So if you've got something you're like, I'm not sure this is going to work, then this is a great time to come to me and say.
It's not like more of what I'm doing. It's more of I'm having problems with Xilinx, the program, doing some really weird stuff to me here lately on my.
Okay. Then I'll either we'll have to type it in at my desk, or I'll have to come over to wherever you're working.
Because the last project it was doing some really crazy stuff, like taking out automatically taking my inputs out.
I'm not surprised. I've seen Xilinx, like I've said, do a lot of really weird things, and really silly things causing it, like that one where the name, even though Windows says it could be longer than 8 characters, Xilinx never told you anywhere, but you couldn't have it any more than 8
I mean,
characters.
it wouldn't be that either because like all the names are like
Right.
4 or 5
So
characters.
yeah, so that's not part of it. But we'll find it out. Okay? I'm usually,
it might work perfect when I go enter it in this time.
and you know what? A lot of times when I'm coming and looking at somebody's stuff, it works perfect. It's like Xilinx is scared of me or something. I don't know why. Maybe it's a stick. I don't know. But my point is, I'll be around all day. Uh, I'm not going to be even in Charlotte Saturday and Sunday. I've got other things going on. So even if you guys are having trouble Sunday and you're Saturday or Sunday and you're trying to get a hold of me, I'm not even going to be near my computer to help. So
That's like
anyway, okay. Um, now we got down to 10 minutes. Are there any other questions? No other questions. There is, we went, did we go through all the alternate approaches or not?
I think we did.
I think we got partway through this, and then, wait, there's only 54. Here I've got some examples of one-hot encoding, so if you're having trouble with it, look at it. I did, yeah, go through some mealy. I've got plenty of examples of VHDL, so remember those. Use this type, state type is, and signal, make sure you got signals, because you cannot, anywhere in your code inside this process, say Q is equal to not Q. Q1 is not, or Q1 is assigned not Q1. It says, Xilinx says you cannot have an input on both sides of that assignment operator. And you can't have an output on both sides of it. So for those things, you've got to use signals, and then you can assign values to the signals that you would assign to the inputs, and then on the output, after you end the process, you take those signal values and finally assign them to your Q outputs or whatever. You got to do it. So anyway, you got a lot of examples, I think, to work with. The one, okay, we did go through all those. This one is very similar to one I have you guys do in the lab. This one, it does take a little while. I don't remember how many slides it is, but this is an interesting problem. In fact, you probably don't even need a state machine to figure it out, because I figured it out with a state machine, and then I went back, and after looking at it, I simplified it just by observation. This one used to be a big deal in a lot of the classes. I guess faculty figured out that I had this solution out there for you, and so they quit assigning it. But this is a good problem. I don't think we're going to have time to do it now, so let's see. Pardon me. See most of you tomorrow in lab or sometime during the day. Okay? There were 31, and I was showing you also how to do some of these simulations. Okay, nothing else? Go work on these and have questions tomorrow because I won't be able to answer them Saturday or Sunday.
Okay.
Yes, sir. I knew he was going to come up. I just
No, I'm not
he
calling
stopped. He stopped